Hello. In this video, I'll be talking about electric fields, specifically the electric field itself and forces within electric fields. If you have two charged objects, in this case both positive, they will feel a force between them. Same charges would repel. If one of these was negative, again there'd be a force, but it would be attractive. They'd attract one another. When we're considering charged objects like this, individual particles, we model them as point charges. What we do is we consider all of the charge is just concentrated at a small point in the centre. So when I'm going to be measuring distances between charged objects, I consider the distance from centre to centre. That's what I'm interested in. I'd describe, or I'd label up, the distance from centre to centre of charged objects with the letter R. Right. What was first discovered was if you were to double the distance between your charged objects, that's now 2R, actually the force between these is now a quarter of what it was when they were there. That would now be a quarter of the force. So force is inversely proportional to the separation squared. It's an inverse square law. What was also noticed was this. Let's make them both positive. If I was to double one of the charges, I'd get double the force. And then if I was to double the other charge, I'd get double the force again. This has 4 times the force between them as that does. The force is proportional to the product of the charges, Q1, Q2. Now, it's much more convenient if we can actually have an equals in there, come up with an equation. Force equals some constant Q1, Q2 over R squared. This is a constant. This constant K equals 1 over 4 pi epsilon naught. The epsilon naught is 8.85 times 10 to the minus 12 coulombs squared, meters to the minus 2, newtons to the minus 1. This is called the permittivity of free space. Okay, so if you know this constant, you know your two charges, and you know the distance between them, you can work out the force between them. One thing that's worth looking at is this. If Q1 and Q2 are both positive, the force will come out as positive. These will be repulsive. A positive force means repulsion. If they're both negative, again they will repel, but a negative times a negative is still positive. A positive force means repulsion. One's positive and one is negative. A positive multiplied by a negative gives you a negative, and that would mean attraction. Okay, so the positive and the negative doesn't really mean anything when you think about your force here. It doesn't mean the direction, it's telling whether it's attractive or repulsive. Okay, so that's really everything I've got to say on force between charged particles at this moment. Let's have a look at the field, the electric field. Okay, it's a positive charge. There's another positive charge. Right. Why do they feel a force between them? Well, here's why. A point charge will actually create around it an electric field. An electric field around a positive charge would look like this. Something like this, with the field lines coming out in every direction at 90 degrees to the surface. So there's 90 degrees there. That's what the electric field around that charge would look like. Notice the field lines spread out as you go further away. The field lines getting further apart, the field gets weaker with distance. That's why the force between charged objects decreases with distance. Now, what is an electric field? Well, the symbol we would use is E for electric field. The electric field strength, E, I'll write this down, electric field strength is the force felt per coulomb of charge at a point in space. So let's just suppose the electric field strength at this point here is 2 newtons per coulomb. That could be an electric field strength. It also has a direction. That the electric field has a direction, so the direction of that field would be that way. So an electric field in general, it's just a region of space in which charged particles feel a force. So if I was to, at that point in space, put a +1 coulomb, it means that every coulomb 2 newtons of force would be felt. This charge would feel a force of 2 newtons away from this charge. If it was there, I might think of the force. If there's nothing there, I might think of the field at that region in space. If I was to put a +2 coulombs there, the force at this point in space, due to this charge here, is still 2 newtons per coulomb. But I have 2 coulombs there, so now this would feel 4 newtons of force that way. 2 newtons per coulomb. Every coulomb feels 2 newtons. So it'd be 4 newtons of force there. Hopefully this shows why the force between charged particles is proportional to the product of those charges. I've doubled the force, I've doubled the charge, I've got double the force there. Now, what if I had a negative? Just flip it over. Well, the answer would still be 4 newtons, but negative charges feel a force in the opposite direction to the field. So that would now have 4 newtons that way. So when you go to draw a field around a charge, field lines come out of positive charges. A positive particle feels a force in the direction of field lines, but a negative particle feels a force in the opposite direction to field lines. So if I was to draw the field around a negative charge, that's right, you've guessed it, it would look exactly like that for a positive charge, but in the opposite direction. So here, a positive charge would again feel a force along field lines. It would move towards the negative. It would be attracted. Now, there is an equation for electric field, and that's what I'll look at with you next. That's how you draw your electric fields and what it actually is. Once again, I'll just reiterate. An electric field is a region in space in which charged objects feel a force. The electric field strength at a point in space, that's the force felt per coulomb of charge at that point in space. If I wanted to work out the field strength at some distance away from a charge, again, I need to know how far away I am from the centre of the charge. And the equation is this. E equals K Q over R squared. Very, very similar to the force equation, which was F equals K Q1 Q2 over R squared. Again, remember K here is 1 over 4 pi epsilon naught. All you do is divide the force by our charge and you'll get your field strength at that point in space. Whereas I think it's actually better to think of it the other way round. If I know my field strength here, all you have to do is multiply the electric field at that point in space by the charge you put there, and you will work out the force that this charge feels. These equations are in the physics data book. This one's not. But it's very useful. If you know your electric field strength at a point in space, multiply by the charge you put at that point in space, and it will tell you the force felt by that charge.